I hope you are here with a beautiful smile and want to learn something new. If not so, then it's time to smile and start this lecture. So in the last class we talked about what is non-inertial frame and all. Today we are going to talk about how some pseudoforce acts on a particle when it is present in a rotating frame of reference, which is a non-inertial one. So the example of this non-inertial frame or rotating frame of reference is our Earth. And we know that our Earth is rotating with a constant angular velocity. That's why our duration of a day is 24 hours always, never 23 or 26. So we are going to now derive some mathematical equations, see some reference frames, and this is our today's agenda. So let us suppose this is a inertial frame of reference S with x, y, z coordinate axis, and this is another reference frame S dash, which is a rotating one. It is rotating with an angular velocity omega, and here its coordinate axes are x dash, y dash, z dash. We know about relative velocity, right? What is relative velocity? If I am traveling with 60 km per hour in each direction and my friend is also traveling but with 30 km per hour velocity in each direction, then my friend's velocity for me will be minus 30, right? Because for me I am at rest, I am not traveling. Let me make it clear for you by drawing some pictures. I am traveling with 60 km per hour. My friend is traveling with 30 km per hour. Let us say this is A and this is B. I am trying to find velocity of B with respect to A. So velocity of B with respect to A will be velocity of B with respect to ground, means from a inertial frame of reference minus velocity not inertial means a frame at rest minus velocity of A from ground frame, means what is the actual velocity with respect to ground. So this will be velocity of 30 minus 60 equals to minus 30. I feel I am the actual situation for a person from or observer on the ground will say that this person is going with a higher velocity and this person is also traveling but with a lower velocity. Both are traveling, but for A will say that I am at rest. This observer on the ground is traveling with 60 km per hour in the opposite direction of this, means towards this means if I am traveling towards east, the observer on the ground is traveling towards west with the same velocity, and B is not traveling with 30 km per hour towards it, but A will feel that it is going towards west with a 30 km per hour velocity. Means we have here the equation velocity of B with respect to A will be velocity of B, means actual velocity minus the opposite velocity of A. Now here we have a equation velocity of B with respect to A equals to velocity of B with respect to ground minus velocity of A with respect to ground. Or we can just erase this ground and say that this is the velocity of things or some vehicles from a frame at rest. So let us suppose this particle is in S frame, and at rest with respect to this S frame. Then from a point of view or from the reference frame S dash, we will feel that the velocity of this particle from rotating frame of reference, I am representing with this R subscript, equals to actual velocity, means its velocity from the frame of reference of S will be equals to velocity and from S frame, which I will represent with a I subscript, small I, inertial one, minus this. We are saying that actual velocity of B minus velocity of the observer from A reference. So this velocity will be equal to omega cross R, which is the velocity of this rotating frame, linear velocity of this rotating frame. Because we are dealing with everything in linear terms, so we cannot put omega, the angular term. So we are going to convert it into a linear term, that is linear velocity omega cross R. So instead of saying S dash, here we are saying that velocity of the particle from this S dash frame will be equals to its actual velocity minus velocity of this reference frame, rotating reference frame, right? Let me repeat it once again to make it more clear. So we are saying that velocity of this particle is equals to its actual velocity of this particle from S dash. A frame which is rotating will be equals to its actual velocity minus the velocity of this rotating frame of reference, which will be omega cross R. It is just some basic things from your 12th and 11th class, I don't remember in particular. So we know velocity is a derivative of position, right? So let us say that this is position P. We can say that position, I am representing the position vector with R, dr by dt from rotational reference frame equals to dr by dt from inertial reference frame minus omega cross R, which is linear velocity of this S dash frame. So here let me erase all these things. Here I am going to put blank space for R and provide you a beautiful equation that is known as operator equation. What is this? This is an equation where we can put variables instead of r, such as velocity or acceleration, and see this equation being worked. So means this is true for all other variables including r, such as velocity and acceleration. So here I am going to put velocity vector for now. Here the position are with respect to the non-inertial frame. So with respect to inertial frame. So I am also going to put value of velocity with respect to inertial frame. That will be just like this, dvi by dti minus omega cross vi. From this equation, you can say that dr by dt is velocity, right? So velocity from rotational reference frame equals to velocity from, as seen from inertial reference frame, minus omega cross r. So here we can put velocity using this equation. So here I am going to say that this will be, derivative of velocity will be acceleration. We will simply say that acceleration AI from inertial reference frame will be equals to dvi by dt from rotational reference frame plus omega cross vi. Now I am going to put the value of velocity as seen from inertial reference frame using this equation. So here vi equals to vr plus omega cross r equals to d by dt vr plus omega cross r equals to omega plus omega cross vr plus omega cross r. Now we have to solve this. Equals to dvr by dt as seen from rotational reference frame plus this here it is plus, so we can differentiate it differently and just add them up. So here d omega cross r by dt plus omega cross vr plus omega cross r, right? Yes. So I am just going to erase it. You write it down. Here we are going to solve this equation now. This is AR acceleration as seen from rotational reference frame as derivative of velocity is acceleration. Now solve this. Here first we will keep r constant d omega by dt cross r and then keep omega constant omega cross dr by dt seen from rotational reference frame plus omega cross vr plus omega cross r. So here this term will be 0 as the earth is rotating with a constant velocity and uniformly rotating frame will have no angular acceleration and d omega by dt leads to angular acceleration. But if this term was present and we use this acceleration for and multiply this acceleration with mass and go for a force, then the force will be known as Euler's force. And this is not our topic now, we are just going to discuss about this. So here AR plus omega cross dr by dt from rotational reference frame, which will be velocity. Derivative of r is velocity. That will be omega cross vr plus omega cross vr plus omega cross r, which will be equals to AR plus 2 omega cross vr plus omega cross r. Let's keep AR in LHS and AI minus 2 omega cross vr minus take both of this term to LHS and reverse this equation so that the equation will look beautiful. I am reversing I have reversed here. You can do these things like AI minus both of these terms equals to AR and then reverse it. I am doing it in one step. Minus omega cross r. Here is acceleration. I am just going to multiply mass in both of the sides. On by multiplying mass on both of the sides, there will be no difference. So I am just going to multiply mass, and after multiplying mass we will get some forces. Here force as felt from a rotational reference frame will be equal to the force, actual force applied, that will be seen from inertial reference frame, minus this term into mass will give us Coriolis force. And omega cross r. Let us don't consider cross for now. Then this will look something like omega square r. And if we will multiply m with this, it will look something like m omega square r. And we know that m omega square r is our centrifugal force. So instead of using r and I as subscript, we are going to use a usual notation, that is dash and a normal alphabet, to represent inertial frame and non-inertial frame. So force experienced from a non-inertial frame will be F dash equals to the actual force F as experienced from an inertial reference frame minus Coriolis force, that is m omega cross Vr minus the centrifugal force, that is m omega cross r. We can say that this is the total pseudo force and denote it with F naught. And here the things are covered, that we will experience a centrifugal force even if we are sleeping on our bed, and we will experience a Coriolis force if we are traveling to somewhere on our flight. So now it is here we can see that if this is Earth, the Earth is rotating with omega angular velocity. We are talking about this position, r position vector, and has latitude phi, means its position vector makes an angle phi with the equator. So here let us say that vertical axis means we can also see it from a ground reference frame, that say your ground and say that this axis means here it is x axis, and horizontal axis as z, your ground as z axis. Then the third axis will be this axis, right? X, here it will be something like cross, like that of our magnetic field. We represent cross to show that the thing is it is directed inwards. So here the y-axis is inwards, and say x is vertical axis, z as north direction, and as this is north, this y will be east. Here omega is just like this. Let us make a parallel axis with the equator. Then you can see that this is the angle phi, and so this is 90 minus phi, and this omega makes an angle phi with the z axis. So we can say that omega makes an angle phi with the z axis. So the components of omega will be something like omega vector equals to omega cos phi, z axis means k cap direction, plus omega sin phi I cap means vertical direction. Here we have omega vector and r vector, and if your velocity is along horizontal, then it is along z axis, and if you are traveling vertically, then it will be x, means I cap direction. So using this you can solve this. I will give it to you as a homework. If possible, I will explain it in the next lecture. So this is for today. In the upcoming lecture, we are going to talk about Coriolis force, free fall, Foucault pendulum and all. Till then, keep watching. Thank you.